Hello guys, welcome back to Zone African Motives, working on our mathematics N5 revisions for the August 2023 exams. We shall be focusing on our question number 3, which is the applications of our derivatives. In this case, we've got first part of question 3, which is 3.1, whereby we are given the function, in this case, of f of x being equal to x cubed plus x squared minus x plus 7. So the first part of our question, which is 3.11, was to determine the coordinates of the turning points of f of x. All right, we are dealing with the coordinates of the turning points in this case. All right, so let us have our function and see how we're supposed to have this question attempted. So remember, we have got our f of x in this case, which is being referred to as x cubed plus x squared minus x plus 7. And the first part of our question was to determine the turning points in this case. How are we going to have our turning points? All right, so we understand that whenever we're dealing with turning points, these are maximum and minimum values. And whenever we're talking about maximum and minimum values, the derivative of that function with respect to x must be equal to 0. So that is the condition of our turning points. So we're simply going to differentiate our f of x in this case, then equal to 0. All right, so what is the first derivative of our f of x? 3 here is going to multiply, that's a 1. So you're going to have 3x squared. All right, then now we've got 2 and 1 here, which is going to give us 2x, negative 1x. In this case, is going to give us negative 1. 7 being a constant is going to be a 0 in this case. So this is our f of x. So this f of x, this first derivative, which is f prime x, must be equal to 0. So we're going to take the first derivative, which is 3x squared in this case, plus 2x minus 1, then equate now to what? To 0, so that we obtain the values of x at the turning points. That is how we're supposed to have this. So using your quadratic formula or your factorization concept, you're supposed to find the values of x. In this case, we could even use factorization. If we multiply the first term and the last term, we get negative 3x squared. So what we need in this case are the factors of negative 3x squared, negative 3x squared in this case, which is going to add up to positive 2x. So we can refer to 3x and negative 1x. If you multiply this, we get negative 3x squared. If we add these two, we obtain 2x. So these are the ones that we are going to replace into the middle term where we have our 2x. We are going to have this as 3x squared. So we shall have this as 3x squared. In place of 2x, we are going to substitute our terms, plus 3x and minus x, plus 3x minus x minus 1 must be equal to 0, or you just use the quadratic formula at once. All right, so factoring out this, we have got 3x, which is common. So you're going to factor out 3x squared by 3x, that's x. 3x and 3x is going to be a positive 1. Here, negative 1 is common. So you can factor out negative 1, we remain with the x plus 1 equal to 0. So at the end, these two brackets are common. So we are supposed to factor out the common bracket in this case. And what are we remaining with? We are remaining with 3x. Here we are remaining with minus 1. So this is going to be 3x minus 1, which is equal to 0. So obtaining our values of x from each bracket, we are going to have our x being equal to negative 1, or from this bracket, our x is going to be equal to 1 over 3 in this case. So these are the values of x that we have at the turning point. So we've got the first value of x, and we've got the second value of x at the turning point in this case. So remember, it's a point whereby you're supposed to have this in terms of x and y. So meaning to say, with the value of x, or with the values of x that we have at the turning points, we are supposed to substitute these values back into the original function, which is our f of x in this case. So we substitute back to the original function. Where there is x here, we are going to substitute minus 1. Where there is x, we are going to substitute 1 over 3, which are the values at the turning points, the values of x at the turning points in this case. All right, so this was going to give us the first turning point, when x is equal to -1, we are going to obtain the value of y there as a +8. You substitute into the original function. And our second turning point, when the value of x is 1/3, the value of y there was going to correspond with 187 over 27. So just also confirm with your calculator to see if we are obtaining the same values, but that was the condition that we're supposed to have in this case. All right. So with this part, that was it. First part of our question. And the second part, which is on 3.12, now they want us to draw a table of x and f of x, where x ranges from x is equal to -3 up to +3. So here we are simply substituting the values of x into our f of x. That's how we end up with this table. So this one is just a direct table that we are just going to have here. So let us see what we're supposed to have at the end. So that is 3.12. So like I said, here we are just drawing our table corresponding the values of x and the values of our f of x, whereby the f of x represents the values of y. So if for the values of x and the values of y, which is the values that are corresponding to f of x in this case. All right, we are told that these values, they should be taken from x is equal to -3 up to x is equal to +3. So we are simply having our values from -3. We move on to -2, -1, 0, 1, 2, and 3. That is what we are going to have on our table in this case. So with these values, what we are simply doing is to substitute into the original function the value of x, which is -3. We substitute into the original function in this case. All right, so what I'm simply saying is that if we have a calculator, I'm just going to show you what we're trying to say. We've got x cubed, so we are going to substitute into the original function our value of x there. That's -3 to the exponent of 3, my plus x squared. So we're going to have plus our value of x, which is -3 in a bracket like this squared. All right, minus x. So it's minus like this. You open the bracket for our x, which is -3 in this case. Remember, our x is -3. All right, plus a 7 in this case like this. So we're going to obtain -8. So the first part is going to give us a -8. You do that for the corresponding value. So instead of rewriting, you just check this with the arrow. Where there's a bracket here, you change. Now it's -2. So you delete this, you put -2. You move on with this arrow until you get a 3. You remove that 3, you put a 2 because it's now -2. Instead of you rewriting, all right, you can just have this. Where there's a 3, you remove that, you put a 2. That is going to give you a 5. So you're going to do this and so on up to the last value where x is equal to +3. All right, so this one was going to give us a +8. This one was going to give us a 0. This one an 8. 2 was going to give us 17. 3 was going to give us a 40 in this case. So these were the values that we're supposed to have by just substituting on our calculator the values of x that are corresponding. 3.13, draw a neat graph of f of x between these values. Show the turning points. So between the values of x to -3 to x is equal to +3, that is where we are supposed to draw this graph of f of x. So as you can check from our graph of f of x here, we can see that it's a cubic function, whereby here a coefficient of x cubed is a positive. And when it is a positive, it means our graph is going to be going up to the positive. All right, so we're going to have this shape. If it is a negative, our graph is going to be going to the negative. It starts from the positive, it goes to the negative like this. All right, but here we are having the coefficient of x cubed being a positive. So our graph is going to start from the negative going up like this. So this is the shape that you're going to expect. And having your values here, we're just gonna have just going to have it as a sketch here. I just hope you see it and understand properly. So we are just gonna have our values for the y and the values for the x in this case. All right, so this is our x-axis, this is our y-axis, our x being taken from 0 to +3 on this side. So that's 1, 2, 3, and so on. And here we've got -1, -2, -3. So you just put the scale on the graph, which is properly here. I'm just doing a sketch. All right. So on the Y, in order for us to obtain a 40 in this case on positive, we can try to use even 5, 10, 15, and so forth and so forth. All right. So meaning to say here, I just need to increase a little bit here, because there is a maximum, the highest possible value that we are getting there. We are reaching a 40 there in terms of Y going up there. So we can just try 5, 10, all right? 5, 10, 15, 20, 25, 30, 35, and a 40 there. So that is what we can end up with. Then here we do the same thing on the Y, -5, -10, -15, -20, and so on and so on. But here we do not need much because the least value is -8. So we just need few values there. So what you're going to do is to mark the points that are corresponding, all right? -3 and -8. So -8 is approximately there on Y. So where they meet, you mark a point. -2 versus 5, where they meet, you are going to mark a point. -1 versus 8, where they meet, you mark a point. You do the same thing, 0 versus 7, where they meet, you mark a point. Maybe it's somewhere here. Let us just say our -1 versus 8. Let us just make it a little bit up like this. All right, you mark a point. You move on to that's 0 versus 7, 1 versus 8. You mark a point again on top. 2 versus 17, that is above 15, approximately there. 3 versus 40 there, you mark a point. So with these points, we're supposed to join them, but noting that, remember, we have our turning points there. The turning point at -1,8, which is the same point as this one that we have also on our table here. We've got -1,8, this point, which means we've got a turning point there. So this point that we see here, -1,8, this one, it's a turning point. Here we are supposed to have a turning point. And we've got another one at a third versus this. A third, it's 0, which means it's approximately just 0,333 below 1. So meaning to say there's supposed to be a turning point just before here. So when you are drawing, you must keep that in mind to say there's a turning point there. So we're going to have this to the turning point. So once the graph reaches the turning point, it is going to be tending to go down now. So it's now going down to this point. And remember, I said there's supposed to be a turning point somewhere there. So as it is going down, it must reach a turning point. In this case, it must reach a turning point from this point. Then the graph goes up. So the graph is now going up, right? Just you're supposed to have a neat graph, guys, a neat one, all right? But as for me, that is how it's supposed to be like. All right, whereby here we have got a turning point. Remember, we said this one is a turning point at 1/3 versus 187. So this is at 1/3 versus 187 over 27 in this case. This one is a turning point. And we have also this as a turning point, which is at -1,8. -1,8 is also a turning point. All right, so this is our graph for f of x. That is how it was supposed to be like. Remember what I referred to, the shape, it's a positive, so it is going up. So as you can see, this graph was going to have one solution approximately at this point. We do not know the exact value there, but what it simply shows us that is that it was going to have one solution. So that is where you end up now with the application of the Newton's method in this case, whereby now you are finding the exact values in this case, like what we are given on 3.14. All right, so let us check what they are now asking us on 3.14 about this better approximation. We are now given to apply or to use one root of the equation is given. So we are given this equation whereby this whole part here is our f of x. If you check, this is our f of x in the original place. So they are saying the root of this equation, our f of x, is close to -2,7. As we saw on our graph, it was close to -2,7. Use the Taylor's use Taylor's or Newton's method once. Take note, we are applying this method once to determine a better approximation of this root, correct to 3 decimal figures in this case. All right, so we are going to take our f of x in this case, and the first solution, which is our x naught, which is 1,7. All right, so this was going to be 3.14. So x naught in this case is the first value that we are given of negative 2,7. So we are given this as negative 2,7 from our f of x. Remember, our f of x was given as x cubed plus x squared minus x plus 7, which is this part of our function. So how are we going to use this function, or how are we going to apply our Newton's method in this case? Remember, it states that x1 is equal to x naught minus f of x naught in this case over the first derivative of x naught in this case, which is taken from the formula that states that x of n plus 1 is equal to xn minus f of xn over the first derivative of xn in this case, whereby this is a 1. On this other part, you are simply, if it is n plus 1, you're simply subtracting 1, it becomes n. So if this is 1, you subtract 1, that's a 0, a 0, a 0, whereby we need our first derivative. Remember, we obtained our first derivative before, so it's just a matter of substituting here. Remember, our first derivative was 3x squared plus 2x minus 1. So what it simply means, on our first derivative here, we are going to substitute the value of x, which is going to be f of minus 2,7 in this case. Wherever there is x, it means we are going to substitute minus 2,7. So what am I trying to say? Let us see on our calculator here, where there is x. So this is x, which is minus 2,7. So we've got minus 2,7 like this to the exponent of 3. All right, then plus x squared. So it's going to be plus our x, which is minus 2,7. So we've got minus 2,7 like this to the exponent of 2. Then minus x, so it's minus our x, which is negative 2,7. So that's negative 2,7 in this case, plus a 7. So this is what we're supposed to have, which is going to give us negative 2,693. All right, so we are going to obtain negative 2,693. This is the value that we are obtaining from our what? From our f of x, the original function, when x is minus 2,7. We do the same thing for the first derivative in this case. So we're going to say for the first derivative, our x again, it's at minus 2,7. What is going to be our equivalent? So in this case, we are dealing with this function of the first derivative. So it's 3 into the value of x, which is minus 2,7. So that's minus 2,7 in bracket squared. All right, plus 2x. So we are going to have plus 2 into our bracket, our x being minus 2,7 in this case, like this, minus 1. So this is what you're going to have at the end, which is going to be 15,47 in this case. So you're going to obtain 15,47. So with these values that we have obtained from our f of x and from our first derivative, these are the ones that we are just simply substituting into our formula, taking x naught as the first approximate value that we're given. So this, we are using our method once. So we are going to have our x naught. Remember our x naught, that is negative 2,7 in this case, minus f of x naught, which is f of x naught. Remember, this is our x naught, which is negative 2,7. We got this value here. So this is the one that we're going to have, which is minus 2,693 in this case. Everything over the first derivative of x naught, knowing that our x naught is minus 2,7. So we're going to obtain 15,47 from there. So this is the whole part that you are supposed to simplify now. So that means our first solution, our first approximate value in this case could be taken from this formula. So from our calculator here, we are going to have negative 2,7 minus, so you're going to subtract, in this case, open a bracket, in this case, have a fraction. So we are going to have negative 2,693 like this, everything over 15,47. So this is 15,47 like this. All right, close that bracket. We have the value of x not closer, which is negative 2,526 to 3 decimal place. The 9 is going to change this 5 into a 6. So it's going to be negative 2,526. So that's negative 2,526 in this case. All right. So that's how you apply your calculator. In this case, that's how we simply use our calculator to simplify this whole situation that you're given. So as you can see, all we need in this case is to know the concept here of finding the values of f of x and the corresponding, the first derivative of that f of x at the given point where you are given as your starting value to say your x naught is this value. And if they said you are going to apply this twice, meaning to say you're going to have the formula for x2 as x1 minus f of x1, everything over the first derivative of x1. But in this case, they said we are supposed to use it once. So we are supposed to end at x1. All right, so that was our Taylor's method in this case. Let us check 3.2, which is the application of maximum and minimum values in this case on our applications of derivatives. We are given that the sum of two positive numbers is 18. The sum, meaning to say if we add two numbers, let us just take, let's say, okay, let's say the numbers are, in this case, the numbers are x and y. All right, these are the two numbers that we are referring, x and what? And y. The positive whole numbers. We do not know these numbers. So they are saying the sum of two positive whole numbers is 18. So meaning to say if I add these two whole numbers, I'm supposed to obtain 18x plus y is supposed to give us an 18. All right, that is the statement they are saying, whereby x and y is representing what? The whole numbers. All right, so we are saying let these whole numbers be x and y, then we add according to the condition that you're given. Then now they're saying, take note about this part. One of these, take note from this statement, one of these numbers is multiplied by the square of the other. One of these numbers is multiplied by the square, meaning to say we can choose to let x multiplied to the square of y like this. That is what they are saying. One of the number x multiplied to the square of the other, or we can choose to let x squared multiply y. X is a square multiplying y. So this one is a condition of your choice that you're going to take between these two conditions to say, is it y, is it y squared that is multiplying x, or is it x squared that is multiplying y, because we are just with one of the numbers in this case. So the question now is, find the numbers that will make this product a maximum, this product of these two numbers. Okay, so in this case, let's say I'm going to use this one. Okay, I'm going to use the first one that I've indicated, but you choose any of it. It's your choice, this one. All right, so our product in this case, we obtained that our product is equal to x times y squared. That is the product of one number to the square of the other. The product there, one number, one of the numbers is multiplied by the square. The square means at that number raised to the power of 2. Now they want us to find the numbers that makes this product a maximum. The word maximum there is the one that is we are working with, maximum. We know that for each condition to be a maximum, it means the first derivative of that function must be equal to 0. Which function are we talking about? The product. They are saying this product must be maximum. So what is the condition that will make this product to be a maximum? As we can see, our product, it's in terms of x and in terms of y. So in order for us to have a maximum value, if we are having a function of x, we simply, the derivative of that function is equal to 0, just like the turning points. So meaning to say we are supposed to write our expression or this product expression in terms of one variable, in this case, either X or either Y. So it is easier for us here to substitute X, an expression that is representing X, because if you check, X is a linear expression. Y is being raised to the exponent of 2. So once you substitute whatever that you're going to substitute, you're going to open brackets and raise that to the exponent of 2, which is a lot. So instead of doing that, we are going to obtain an expression that represents X, but in terms of Y. From where? From these two numbers, where we are told that if we add these two numbers, they must give us 18. And what we want from this equation is to have X, because it's easier for us to substitute. So we are going to make X the subject. X is going to be equal to 18 minus Y, transpose Y to the other side. So meaning to say, this is the expression that represents X. So in place of X, we are going to substitute now, meaning to say our product now can be given as X, which is 18 minus Y. So this is 18 minus Y like this, times Y squared. As you can see, this expression of our product is now written in terms of Y only. So we can find the derivative and equate. Just like if it is written in terms of X, the first derivative with respect to X must be equal to 0. If it is written in terms of Y, the derivative of Y must be equal to 0. So meaning to say, we can simply write in this short our product, which is representing P, in terms of Y. So you can just write as PY like this. That is the product of the two numbers, but in terms of what? In terms of Y. Okay, expand. Here we are going to have 18Y squared. Y squared times minus Y, we are going to obtain Y cubed in this case. So this is the expression of the product of our terms in terms of what? In terms of Y. And they are saying this product that we see in terms of Y must be a maximum. What is the condition that will make this product to be a maximum? That is the condition whereby its derivative must be equal to 0. So since we have this expression in terms of Y only, we can determine its derivative. That means we are going to say the derivative of the product in terms of Y must be equal to 0. This is the condition that we want. So let us determine our derivative of the product in terms of Y. So the derivative of the product in terms of Y is going to give us what? Multiply this one, we are going to obtain that will be at 36 there. So we're going to obtain 36y, 3 times 1, that is going to be minus 3y squared, like this. All right. So this is the expression of the product, of the derivative of the product. And we are saying the derivative of this product should give us what? Should give us a 0. That means we are going to take this derivative of 36y minus 3y squared, equate this one to 0. That's an equation that we have formulated in terms of Y. So we are going to solve this equation. Never be tempted to divide by 3y. If it is an equation, you factor out the 3y in this case, which is common. So it's 36 divided by 3, which is going to be 12y, and y is going to cancel. 3 and 3 cancels here. Y squared divided to y is going to be a y, which is equal to 0. So we know that from this concept, the 0 concept, the product, if it is giving us a 0, it means 3y must be equal to 0. So if 3y is equal to 0, or 12 minus y must be equal to 0. So from this one, y gives us a 0, or from this one, y is equal to 12. If you take y this side, y will be equal to 12. But remember, we are talking about a condition whereby this product, it's a maximum. This product here, it's a product. Take note, our product is of x and y. So if y is a 0 here and you multiply, you are going to get a 0, which is not a maximum value. So meaning to say our y cannot be equal to 0, because if y is a 0 here, whatever that you're going to multiply at the end is going to give us a 0. So that means we can't let y be equal to 0 in this case. So y cannot be equal to 0. We are going to take our y being what? Being 12. This is a value that can give us a maximum value. So you compare when you are given two possible values like this. So having the value of y, we need now the value of x, because this product is of two numbers. It's a product of x and y squared. So at that moment, the x, remember we said it can be taken from expression x is equal to 18 minus y. So knowing that from our expression, we are saying that x is equal to 18 minus y like this. We are simply going to substitute x is equal to 18 minus y, which is 12, in this case. So our x is going to be equal to what? Is going to be equal to 6. All right. So this is what you're going to have. If we use this number, x is going to be 6, y is going to be 12 in this case. So we are simply saying in this case, these are the two numbers that we are talking about, the whole numbers according to this condition. So it's either of these numbers can be 6 or can be 12. This is not like it is like that. It depends with the condition that you are talking about, but one of these numbers must be 6 and one of them must be 12. But according to this one that we work with, x must be 6 and y must be what? Must be 12, so that we obtain a maximum value. And if you add 6 plus 12, you can get 18. So if they were asking us to calculate the maximum, here they want the values, find the numbers. Sometimes they might ask us to calculate that area. So you simply substitute those numbers here. In place of x and y, you substitute the numbers. So that was the condition. All right, so here, that is how we're supposed to answer our question. 3.3, we are given that sand is being poured onto a surface. So we are pouring sand on a surface at 15 cubic centimeters per second. This is not just written for the 15 cubic units per second, cubic centimeters, it can be cubic meters. We are talking about volume per unit time. So there we are given the derivative or the rate of change of volume with respect to time. Remember, volume is measured in cubic units. So that is how you tell. So this one is 15 cubic centimeters per second. It is forming a conical pile in this case. So meaning to say this, when it is being poured, it is forming a shape of a cone. That is a conical what? Pile. It is forming a shape of a cone, whereby we know that from our cone, we've got the perpendicular height and we've got the radius in this case. So it is forming a cone at the end. But in this cone, we are given which the base radius is always, take note, always the base radius is equal to half of its altitude. The altitude in this case is the height. That is our altitude in this case. We are representing what? The height. So in this statement, they are said in every condition that is going to happen, the base radius, which is our r, is going to be always equal to the half of the altitude. So that is half of what? Half of h, which is going to be h over 2. So always r is equal to h over 2. That is what we're given. Then the question is, how fast is the altitude? How fast is the altitude? What are we talking about? The height. How fast is the height of the pile increasing? All right. So whenever I talk about how fast, it's a rate of change. The rate of change of what? Of the out. What is changing here is altitude. So they want to know how is the height changing with respect to time. That is a rate of change. How fast is it changing? Knowing that if we have got cubic centimeters for volume, our height is going to be measured in centimeters. So we want the rate of change that we do not know in this case in centimeters per second. That is the rate of change. How fast is, if they said how fast is the radius, meaning to say we're supposed to talk about the r, the t, the radius, but here they are talking about how fast is the altitude, and we said our altitude is represented by what? By the height. How is the height changing with respect to time? How is it increasing? All right, but we are given a condition there. When the pile is 3 meters high. 3 meters high, we're talking about the height. That is 3 meters high, or they can say 3 meters deep. It's also depth, and being high is the height of that particular cone that we are given. So we are given at a condition whereby our height is what? Whereby the height at that moment is 3 centimeters. How is it going to increase? And we have a hint of the volume. Always check the volume if it corresponds. Sometimes they might make a mistake on typing this formula, but here in this case, that is the correct formula for a cone. The volume of a cone is given as a third pi r squared h, that is a third base area times the height, all right, times the perpendicular height. So knowing this condition, we want to know how is this height going to increase per unit time. So I said, guys, whenever you are dealing with the rates of change, you formulate from the volume that you are given, the change of the volume. This is the basic unit, or from area, because the volume is the one that can be written in terms of the radius and in terms of what? In terms of the height. So meaning to say, you ask yourself, how did you formulate this volume that you are given in this case? How did you formulate? We formulated from dV dt, which is equal to what is affecting our volume. It's affected by the height. The height is the one that is affecting. So it is going to be the derivative of the volume with respect to the height. What is affecting that volume? If it is radius, it was going to be the derivative of volume with respect to the radius, times that part that is affecting our volume, but with respect to time. Now, if it is radius, it is going to be times dr dt in this case, so that these two must cancel. You remain with the dv dt, which is this one, dv dt. If these two are not canceling, these ones, like this part, dr like this, must cancel, so that you remain with the dv dt. So the formula that you are using here, it depends with what the volume is going to depend on. Here, it's affected by the height. So meaning to say, we are going to take the formula that has got the height. So this one, we are not going to use it. So this is the formula that gave us this dv dt. We have this dv dt. We have it here. What about dv dh? It means the derivative of volume with respect to the height. So where are we going to have it from? This one, we can obtain it from our volume. Remember, our volume here, let us work it aside here. Remember, we are given that our volume is equal to a third pi r squared h. And we are given here, we want to find the derivative of volume with respect to h. But here there's a radius. So meaning to say, we must write this radius in terms of h. And we are given that radius always, it is equal to h over 2. So meaning to say, our v was going to be a third pi, the radius, which is h over 2 squared times the height. All right, so you're substituting so that you make dv dh, it must be an expression for volume with respect to the height. All right, so v is going to be a third pi, that is h to the exponent of 2 was going to give us h squared over 2 to the exponent of 2, that was going to be 4 times h, which is same as h over 1. So we multiply the numerators together. So this was going to give us 1 over 3 times 4 in this case, which is 12. So it was going to be 1 over 12 pi h squared times h. This is to the exponent of 1. You simply add the exponent. So it was going to be a third pi h cubed in this case. All right. So a third pi h cubed, it's now an expression for volume, which is the same as this one that we had before. But we are now having an expression for volume in terms of the height, so that we can find the derivative of volume with respect to that height, which is h. So that is the purpose of writing this in terms of what? In terms of h, so that now we can find the derivative of the volume with respect to the height, knowing that here we are just going to drop the exponent. So it's 1 over 12 times 3, which is going to give us 1 over 4 pi. You subtract 1 on the exponent, so it is going to be h squared. Remember your derivatives. You drop the exponent, subtract 1. This one, it's a constant. Pi, it's a constant, so you don't differentiate that pi, just multiply by the part that you have. So now we have dv dh in this case. From our information, our dv dh can be given as 1 over 4 pi h squared in this case. So this is the one that we are supposed to have now in this case, because what we want is to find the HDT, this one. So we simply have to substitute and make what we want the subject in this case, because we have dv dt, we have dv dt here, it's 15. So 15 is going to be equal to dv dh, our dv dh, which is the derivative of the volume with respect to the height. In this case, we got 1 over 4. So that is 1 over 4 pi h squared times dh dt, which is the one that we are supposed to find how the height is increasing with respect to time. So in this case, we can just remove this 4 here, multiply by 4 here, multiply by 4 this side. Remember, this whole part is a single term. So once you multiply by 4 here, you've also multiplied here. You don't multiply by 4 by 4. You just multiply once. All right. So this one and this one cancels. So that was going to be a 60 here. So 60 is equal to pi h squared dh dt. Remember, as we want to remain with the dh dt. So what do? We divide by what is affecting our dh dt, which is pi h squared. So the moment we divide by pi h squared, we are going to remain with dh dt, which is 60 divided by what is dividing here, which is pi h squared. So this is an expression in terms of h for how our height is going to increase for any particular value of h that you'll be given, because h is changing. That is why we're saying an increase. So h is affected. It's like it's the value that is changing. So at that moment, we were given that h there, when our dh dt is the one that we are supposed to calculate, it must correspond when h is equal to what? 3. So now we are going to substitute our h, which is 3 in this case. So that means at the end, the rate of which the height is going to increase with respect to our time. In this case, whereby the height is a 3, is going to be given now by 3 squared. This part is substitute, which is going to be what? So you can simplify on your calculator this whole part. So this was going to give us something like 2,122 like that, which is height measured in centimeters. So that's we have it in centimeters per second, because we are dealing with the rate of change of the height with respect to time. So it's centimeters per second. If it is volume, cubic centimeters, because our volume is measured in a cubic unit. So if it is volume, it must be cubic centimeters per unit time. All right, so this is how you play around these typical questions. As you can see, it was necessary for us to know our volume, in this case, an expression that is representing our volume in terms of h. From there, after having in terms of h, differentiate so that we obtain dv dh, because it's needed on our formula. We need dv dh. Already having dv dt, what is remaining now is this dh dt, which is the one that you are asked here. Find it, make it the subject of the formula, substitute the value of the height that you are given at that particular moment. That is how you answer these typical questions for the rate of change. So we have a separate class that we actually did this video. Make sure that you watch it. We are just left to upload those videos, but make sure that you watch them so that you understand more about the rates of change of this particular on this particular section on the applications of our derivatives. But for now, guys, that's it from Meson African Motives. Till we meet again.